So far, we have been covering a lot of architectures, and we were mostly focused on how to train those architectures using our training data. Now we are going to focus on our validation data and try to automatically adjust the architecture. And basically, you're automatically adjusting your hyperparameters. But AutoML is more than that. It's not only about hyperparameters, it's about having systems that are going to generate architectures on their own, or at least trying to do so. I'm going to start with neural architecture search and introduce a little bit of reinforcement learning, but we are going to spend a lot of time next semester on the topic of reinforcement learning alone. So this is just the simplest way or the simplest reinforcement learning algorithm that you're going to encounter. What we have been doing so far was mostly architecture engineering, and previously machine learning without deep learning was about feature engineering. So you would spend a lot of time engineering your features, then deep learning came and you moved from feature engineering to feature learning. So now you're learning your features. But then we saw some problems with that, with deep learning even. You need to think a lot about your architecture. And actually, up until this point in the semester, we have been engineering different types of architectures. Can we do architecture learning and move beyond architecture engineering? There is an answer to it, and this is one of the simplest answers to that problem of architecture learning. We can have a recurrent neural network, and I'm going to tell you why recurrent neural networks. Why do you need them? It's going to output a probability on the space of architectures. And then as soon as you sample one architecture according to that probability distribution, you're going to be able to train it. So now you're going to look at your training data, train your algorithm, write the loss function, train it. It's going to take a while, maybe one day. Now you take your algorithm and look at your validation data, and for instance, measure its accuracy or any other performance metric that you have. That's going to give you R. It's a signal for you to adjust the parameters of your controller, recurrent neural network. So it's going to tell you, yes, this architecture is good, it's doing this much good, or it's bad, it's that bad. And then you're going to adjust the gradients of your recurrent neural network, and then you keep reiterating. Then your recurrent neural network is going to give you another probability distribution because its parameters updated. According to that probability distribution, you're going to sample an architecture, train it, validate it, get your accuracy, update your gradients, and keep doing that. Any questions about the big picture so far? Because I'm going to go into details of the math and how you actually use it.
What do you mean by gradient of P, given that P is a probability?
So your RNN, the same way that when you had your convolutional neural network and it was outputting a probability distribution over your images, over your labels, so you're parameterizing your probability. The same way, you're parameterizing your probability over the space of architectures. So this P is actually parameterized by your neural network. Does this make sense? I'm going to go into more details.
Yeah, I think I got it now. Thank you.
Okay. So P is parameterized by your RNN, and then you keep updating P according to the feedback that you're receiving from your validation data. Now the question is, how do you actually put a probability distribution on the space of architectures? First of all, you need to say, what is the space of architectures? You need to first define it. And then you're going to be able to put a probability on top of that. Let's say you have a recurrent neural network, and this is exactly your controller RNN. And let's say you are interested in knowing what should be your filter height, what should be your filter width. So this is the size of your filter. How much are you going to stride it to the right? How much are you going to stride it to the bottom? And how many filters do you have? So let's say this is the space of architectures. As soon as you know your filter height, filter width, your stride, and number of filters, then you're going to be able to define your convolution. But then this is combinatorially big of a space for architectures, because you can have many numbers for your filter height. Let's say you can have 10 numbers for that. You have 10 other numbers here, just as an example. Up until now, this is 10 to the power 2 choices that you can make. Then you're going to multiply it by, say, 10 other choices. Then it's going to be 10 to the power 3, 10 to the power 4, 10 to the power 5. And this is combinatorially huge of a space of architectures. And this is beyond any human being to be able to control that. So this is the architecture, the space of architecture, and your RNN is going to give you the probabilities. For instance, it's going to give you the probability that the filter height should be 10, or the filter height should be 3, maybe a 1-by-1 convolution or a 3-by-3 convolution. So that's how you're parameterizing it, and you are putting a softmax here. The same way that you are doing it for classification, it's the same thing here. You have a softmax over finitely many choices, another softmax here over finitely many choices, etc. And then this is the way that you're parameterizing your probability. So far, so good. And then this RNN is going to be parameterized. And let's say theta C are the parameters of this model. There are some weights and biases going on here. And then you have a list of actions. This is action 1, action 2, action 3, action 4, action 5. And capital T for this particular example is 5. So you have a list of 5 actions. And each action you discretized it, you can call that tokens. So whenever you hear the word token, that is just integers. So you have 5 or 10 integer choices here, 10 other ones here, etc. And then this is going to give you the architecture that you're trying to find. So I think there is a comment in the chat, a question. Does the model that is put into production just use the architecture components that have the highest probability and at the end of training? So there is no training here per se for finding your architecture for AutoML. You are doing a lot of training and you're looking at the validation accuracy of your models. And the one that ends up having the highest accuracy in the end, you're going to put that in production. So the only catch in your question is that we need to remove that training part and call it validation, the one that has the highest probability at the end of this process. Does that answer your question? Okay, perfect. So now you have a list of actions, and then you're going to sample an architecture because you have an RNN, it's outputting your probabilities. Now you can sample an architecture according to that probability. Now you can go ahead and look at your validation data, and that's going to give you a signal, a reward of how good your model is, how accurate your model is. And then in the end, what you want to do is exactly what you just asked in the chat. You want to maximize the reward. You want to maximize the accuracy of your model on the validation data. And then you are sampling from your probability distribution. So you're sampling from your RNN. And that's going to give you your expected reward function. The rest of the lecture is how you actually do it, because we know that for your reward, it's just a scalar. You cannot do backpropagation through it. It's not parameterized. You run your model, you look at your validation, and that's just going to give you a number of how good that model is. Now the question is, how do you actually maximize this? Does this make sense so far? Okay, perfect. To optimize this objective function, you need to know the gradients with respect to your controller, or at least have approximate gradients. So you need to be able to approximate your gradients, and then you're going to be able to do gradient descent. Let's see. This J function is a function of the parameters of your RNN. You want to take its derivative with respect to the parameters, and that's this term that you're writing here. This expectation is going to give you an integral of R times P, and then we know that the gradient, we can interchange it with the integral under some mild conditions, which are not that serious. So you can do that because expectation is a linear operation and taking gradients is also a linear operation. So you can take your gradient inside your integral. Okay, so far so good. R is a scalar, it's not parameterized, so there is not going to be any gradients on it. The only thing that is parameterized is your probability, the one that you're sampling from. So you can take the gradient of the probability with respect to your parameters. And this is just your RNN. And I'm going to tell you how RNN is going to give you that. Now here is a trick. You can divide and multiply by P. So we didn't do anything. You're just dividing and multiplying. And you can easily cancel those out and get back. And this is the interesting trick that I want you to learn about. You see that a lot in reinforcement learning. The gradient of the log of the probability, it's the gradient of the probability divided by p. And where is that division coming from? It's the gradient of your, or the derivative of the log function. That's going to give you 1 over the argument. So this is also equivalent. The gradient of the log is the gradient of whatever that is inside the log divided by p. Now, what is good about this? This is just expected value. Because you can take p to the right side, and this is the expected value of the gradient of a log times r. Any questions about that line of math? Was everything clear?
Are we purposely leaving out what we're integrating respect to just to keep it general?
It is actually to save some space, to be able to write it in one line. It's with respect to dA, to be precise, because your probability distribution is parameterized and it's acting on the space of actions. So there is dA, but then you can just remove it for the sake of notation. Any other questions? So this trick, I want you to learn. You can divide and multiply by a probability, and then the gradient of a log function is the gradient of the argument divided by p. This we are going to use over and over again in deep learning, and especially in reinforcement learning. Okay. So the cool thing about deep learning and why it is successful is because of two chain rules. The first chain rule is the chain rule that you know from calculus, and that's going to give you backpropagation algorithm to take gradients of complex functions like neural networks. The other one is the chain rule from probability. So two chain rules are behind deep learning. And let's take a look at this. You want to write a probability distribution over a list of actions. According to the chain rule for probabilities, you can just break it apart. You can say, I'm going to take my action first. The second action, there is a probability distribution on it. Then I'm going to go to the next round. I took actions 1 and 2. I'm going to choose action 3. I took actions 1, 2, 3. Now I'm going to choose action 4. So you are conditioning on previous choices. And this is where your RNN is going to come in. A good model is a recurrent neural network for conditioning. So you can basically summarize your past in a hidden layer. And then your recurrent neural network is going to take as input that hidden, you can call that h of t. It's going to take h of t. It's going to take whatever inputs that you have at that moment. In this case, you don't have any. And then it's going to output your actions. So there is a question, that's just a Markov chain, right? No, not really. It's even simpler than that. Markov, you are going to say that you're going to cut your past. But here you have your entire past. You're starting from 1. This is just a chain rule for probabilities. Probability of x comma y is probability of x times probability of y given x. So that's what you have here. But then you have 3 rounds of it. Okay. But then you can summarize the past in a hidden unit, and that's going to give you your RNN. Okay, let's take that formula and plug it inside our gradient. So you're taking log of p of a from 1 up until capital T, and you're using this product. The log of the product is the summation of logs. That's why you're gonna get the summation here. You can take it all the way to the left. Everything is linear and nice. This is where you have your recurrent neural network giving you your actions. You're gonna keep R, and this P, you can get rid of it and write it in terms of expectation. So you're just rewriting a little bit of math. Is everything clear so far? Okay, perfect. Now you can do Monte Carlo estimation to give you your approximate gradient. What can you do? From this RNN, you can sample from this probability distribution. You can sample multiple architectures. In this case, you're sampling M architectures. And you go ahead, train each one of them, and that's going to give you M accuracies. So in this case, K goes from 1 up until M. So you have K different accuracies for K different models. Don't worry about this B yet. I'm going to tell you why you do that. But then the rest of it is a Monte Carlo estimation to this expectation. So this is approximately correct. Okay. Without this B, this estimate is going to have a lot of oscillations. It's going to be an unbiased estimate to your gradients, but it's going to have a high variance. Why is that? Because you want to know if you take an action and if somebody gives you a reward, how good that reward is, relatively speaking, to a baseline. For instance, if somebody, for instance, you guys are in a class, you have an assignment, and then you get a 90 out of that assignment. And then now you want to adjust your behavior for the next assignment. And if I don't tell you what the average grade of the class was, then you're going to think that you did pretty good and then keep repeating your mistakes, okay, for that particular assignment. But if I tell you that most of the class or the average score of the class is 95, then 90 doesn't look good anymore, okay? That's why you're subtracting a baseline. And as I mentioned, M is the number of different architectures that you're sampling. T is the total number of actions. In this case, it is 5. RK is the corresponding validation accuracy for the kth architecture. And B is a baseline. And it's just a moving average of previous architecture designs. And this is basically the average performance of those architectures that you tried out. And this is going to help you still stay unbiased. This is still an unbiased estimation because this is just a constant. You can do some of these arithmetic and get rid of B, and using the fact that the gradient of a constant function is just 0. So you're going to do a little bit of math. It is still unbiased. It has a lower variance as an estimate. Okay, so far so good. So which step are you confused about? Yes, so what you're going to do is you're going to sample M architectures. That's going to give you R rewards. And then you're going to add the average of those rewards to the previous averages that you already had. And that's going to give you your B, the baseline. So think of it as an averaging over time because things are evolving over time. And by time here, I'm not mentioning this time. That's not what I'm referring to. Each step of this cycle is going to give you your time. And in each cycle, you're testing M architectures. And K is just you can sample one architecture from your probability distribution, or you can sample many of them. Oh, exponential moving average is just your current average, maybe 1 minus gamma of your current average plus gamma of the average from this iteration. That is called exponential averaging. So you can just look at Wikipedia for that. It's an equivalent way of computing averages over time for a time series. No, there is not going to be any gradients for B. The same way that there are no gradients for R, there are no gradients for B. For P, there are gradients. So is everything clear now?
So I guess my last question is, how do we maximize the objective function, because we're used to the gradient descent?
Exactly. So as soon as you have the gradients of an objective function, then it's game over because you're going to do gradient descent. Or in this case, you want to maximize, it's going to be gradient ascent. You're going to optimize. You're going to take steps in the direction of the gradients, and you're updating the parameters of P.
Okay, so that's my question. Thank you.
Okay. Any other questions? Okay. Was everything clear? Okay, perfect. I guess we can move on now. This is one of the architectures that are gonna come out of this process. If you want to do image classification, you have your image, then you're gonna have a filter that has a height and width of 3. So it's gonna end up being 3 by 3 convolution. And then you're gonna end up having 36 for the next one. And these are basically your layers. You chose the first layer. Now you're gonna go ahead and choose the second layer. Again, that one is also parameterized by your recurrent neural network. That's gonna give you a 3 by 3, 48, 3 by 3 convolution, 36. And there are also the possibility of having residual connections. First of all, you're gonna say, this is one of these choices that you make. How many previous layers you're gonna look at. And then another choice is which ones from those how many. So for this last guy, you have a lot of choices. You have a lot of layers before it. You're gonna say, I'm gonna look at the one right before me, 2 layers before, etc. 1 layer here and another residual connection there. And if the dimensions don't match at some point, you're gonna put 1 by 1 convolutions. So you're going to manually fix the dimensions or the resolution. You're going to either downsample, upsample, and in most of these cases, it is downsampling your resolution. Okay. Another architecture that's going to come out, you can have a recurrent neural network. You can train it on some textual data. Why am I including this? Because this neural architecture search is a general framework. You can use it beyond images for text and for different architectures. For a recurrent neural network, you have the input at this time. You have some hidden information from the past, which is going to summarize all of your states or all of your decisions before this step. And then there is some memory, which you're going to sometimes add memory to it, sometimes extract information out of it. Sometimes you're going to forget, add information, etc. And then out of these operations, you're going to get the hidden unit from the next state and your memory cell. And this is not an LSTM. This is not a gated recurrent neural network. This is not a basic recurrent neural network. This is a recurrent cell that is coming out of neural architecture search. So there is a question in the chat, is activation function also in the search space? For this particular case, yes. And as you can see, you can have all of those choices that you want. What activation function you want to choose right after your convolution? Should you do batch norm? Shouldn't you do it? There is another question. So each layer has T actions in it, and we optimize J for each layer. For this particular architecture, you can actually have optimize all of them. You can have a single recurrent neural network, your controller, outputting the probability of the filter height in layer 5 to be 5, I don't know, or B3, etc. And then you do it for every single layer. So in this case, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's going to be 15 times 1, 2, 3, 4, 5 choices. That's going to be the list of actions. Okay, does that answer your question? But then the macro structure, there are some choices that you have to make. For instance, how deep you want your neural network to be. It is external information to this process. So you have to choose that outside of this process. And this is exactly goes back to what is the architecture search space. How do you want to parameterize your search space? Any other questions?
What are the C neurons in this recurrent cell displayed?
What do you mean?
The C subscript T-1 and the C.
Oh, yeah. This is inspired by LSTMs. For LSTMs, not only you have a hidden layer, you also have some memory cells. Because there is this problem with recurrent neural networks that you cannot go back too many iterations in the past, because the length of a recurrent neural network is directly specified by how many time steps you have. So a deep recurrent neural network is as deep as the number of time steps. And because of that, there are some vanishing and exploding gradient problems coming on. To train them properly, you're gonna keep a memory, which is this C, that you sometimes add information to it and sometimes subtract information from it. Sometimes you forget, sometimes you remember. And this is gonna give you the opportunity to go really back in time.
So is it kind of like a persistent residual connection, like in the long term?
Yeah, you can think of it as residual connection, but in a recurrent neural network, they're going to tell that it's gating mechanism. You have a forget gate, you have an input gate, you have an output gate. Sometimes you're reading from your memory, sometimes you're writing to it. Okay, but don't worry about RNNs. That's not the topic of what we are doing these days. We are going to do that when we do speech and text later on in the second semester.
Okay, thank you.
Yeah, sure. Any other questions? Okay, so what was the message from this topic? That the search space matters. So you need to first design a search space, then put a probability distribution on top of it, and then keep sampling architectures from that search space.